Hello, everyone. Welcome to this lesson on important statistical inequalities. In this lesson, we are going to discuss three important statistical inequalities, namely Jensen's inequality, Cauchy inequality, and Chebyshev's inequality. Jensen's inequality concerns an inequality on the expected value of a random variable. Cauchy's inequality concerns the expected value. It is an inequality on the expected value uh, in two random variables. Cauchy's inequality is concerned about the probability of a random variable. We will first discuss Jensen's inequality, but before that, we need to know something called the convex function. So therefore, let us first look at the definition of a convex function. A real valued function g defined on an interval I, a real interval I, is said to be convex if the graph g lies below or on the straight line segment joining any 2 points on the graph. So, for example, this is an example of a convex function. For this function, if you consider any 2 points on the graph, say for example, g at x1 and g at x2, and if you consider the line joining those 2 points on the graph, if you consider any x value between the corresponding x1 and x2, the line corresponding to any point on the segment will be above the corresponding point on the graph. Right. So that means the graph will be always below the line segment joining any 2 points on the graph. Right. So mathematically, we can express it as, if you consider, for example, any point on this segment can be written as lambda times gx1 plus 1 minus lambda times gx2, with the lambda being a number between 0 and 1. Right. So gx1 is this point, x1 is this value here, gx2 is this point when x value is equal to x2. Right. So any point on that line segment can be written in this form, lambda times gx1 plus 1 minus lambda times gx2 with a lambda value between 0 and 1. Right. So if you consider the corresponding point on the graph, that can be written as g of lambda x1 plus 1 minus lambda x2, because the corresponding x value here is equal to lambda times x1 plus 1 minus lambda times x2. So the point on the graph corresponding to that point is g of lambda x1 plus 1 minus lambda x2. Right. So for a convex function, always the point on the line segment lambda times gx1 plus 1 minus lambda times gx2 must be above or equal on the line on the graph. The point on the graph. So the point on the graph is g of lambda x1 plus 1 minus lambda x2. Right? So a convex function can be mathematically defined as a function that satisfies this condition for every x1, x2 in the concerned interval I, and every lambda in zero interval. So, for example, if you consider lambda changing between 0 and 1, this point will be changing from here to here. And the corresponding x value is equal to, again, with the same lambda x1 plus 1 minus lambda x2. The point on the graph at that x value will be g of lambda x1 plus 1 minus lambda x2. So if the function is convex, then this point here will be always above the corresponding point on the graph. In other words, the point on the graph will be less than or equal to the point on the line segment. So that's what this says. G evaluated at this point is less than or equal to the point on the line segment lambda gx1 plus 1 minus lambda gx2. This is the same graph, little bit bigger, right? So x1 is here, x2 is here. You are considering any 2 points on in the interval I that you are considering, right? So this is somewhere in the middle, anywhere in the middle. Point will be given by lambda x1 plus 1 minus lambda x2, right? When lambda changes between 0 and 1, this point will change from x1 to x2. So if you consider any point on the chord connecting gx1 and gx2, it will be represented by this kind of point, lambda times gx1 plus 1 minus lambda times gx2. And the corresponding point on the graph will be g evaluated at lambda x1 plus 1 minus lambda x2. So if the function is convex, this point, this value, this y value will be always less than or equal to this y value up to here. So that's what the definition of a convex function. A convex function can also be defined in another way by considering the tangent drawn at any point on the graph. So for example, here I have drawn the tangent to this function at some point x naught. You can see that for this particular tangent, if you consider any x value, the function will be above the corresponding value on the tangent, right? So here above or equal. At this point, it is equal, right? If you consider any x value here, so then the corresponding point on the curve is above the corresponding point on the tangent. If you consider any point here, again, corresponding point on the graph will be above the corresponding value on the tangent. So that is another way. If you consider any other point, for example, if I draw a tangent here at this point x1, again, you will see that the point on the graph for any x will be above or equal at that particular point to the point on the tangent. So therefore, that is another way of characterizing a convex function. An equivalent characteristic for a differentiable convex function is that the graph always lies above any tangent line. So that mathematically can be expressed as, if you consider any point x naught and any value x, then gx, that is the point on the graph, will be greater than or equal to the point on the tangent line at the same point, right? So this is the tangent drawn at x naught, calculated at value x. Right, the value on the tangent at x naught, calculated at value x. So gx is greater than or equal to gx naught plus x minus x naught, g dash x naught. So you can consider this characterization when the function g is differentiable. right? If it is twice differentiable, then we can again characterize a convex function as a function whose second derivative is always greater than or equal to 0. So those are different ways of defining a convex function, right? Right. Original definition is this one, right? For a convex function. But if the function is differentiable once, then you can use this characterization. If it is differentiable twice, you can also use this idea to define a convex function, right? Now, having defined a convex function, now let us look at the Jensen's inequality. Jensen's inequality is preliminary a mathematical inequality, but we can, of course, use it for statistics as well. So I will first look at the mathematical inequality and then go to the statistical version of it. Right. So let G be a convex function defined on some interval, real interval I. And suppose you have x1 up to xn, you are considering x1 up to xn values in that particular interval I. And suppose lambda 1 up to lambda n are non-negative values greater than or equal to 0, some constants, satisfying this condition that the sum of those lambda should be equal to 1. Right. So in the previous case also we were looking at a particular situation, lambda and 1 minus lambda. Right. So then the sum of those two numbers is again equal to 1. Right. So in this case, we are considering n values satisfying sum of lambdas equal to 1. Then if you consider G evaluated at this point, sum of lambda I times xi, that will be less than or equal to the sum of lambda I gxi. So that is what the Jensen's inequality tells you. And particularly the equality here holds if all xi's are equal or if G is a linear function on the interval containing the points x1 up to xn. That is when the equality holds. Otherwise, it's always less than. G of this quantity is less than or equal to this quantity when sum of lambda is equal to 1. Right. Let's just for the interest, let's look at the proof of that mathematical inequality. We can prove this by induction. Let's look at the situation where, because we have to have at least n equal to 2 for this situation. For n equal to 2, Jensen's inequality will be just saying that G evaluated that lambda 1 x1 plus lambda 2 x2 is less than or equal to lambda 1 times gx1 plus lambda 2 times gx2, which is exactly the same as the first definition, original definition of a convex function when lambda 1 plus lambda 2 is equal to 1. Right. So therefore, you can easily see that that is the definition of the convex function, right? For n is equal to 2, Jensen's inequality is exactly the definition of convexity. That means G lambda 1 x1 plus lambda 2 x2 less than or equal to lambda 1 gx1 plus lambda 2 gx2, where lambda 1 plus lambda 2 is equal to 1. In that case, lambda 2 can be written as 1 minus lambda 1. So that's what we used as the definition of the convex function, right? So now let us assume that the Jensen's inequality holds for n minus 1 points. Right? n minus 1 points. That is, whenever you have several constants, say for example mu1 up to mu n minus 1, which are non-negative, greater than or equal to 0, satisfying the sum of those values equal to 1, then this inequality should be satisfied. So suppose this inequality holds whenever you are considering some constants n minus 1 constant satisfying this. Suppose this condition is satisfied. Then we are assuming that this condition is satisfied for any constant satisfying, any n minus 1 constant satisfying this condition, then we should be able to prove that the inequality holds for case n with n points. So let us consider that situation. So now let us consider x1 up to xn points in the corresponding interval I that we are considering. And suppose lambda 1 up to lambda xn are some n non-negative values satisfying this condition. Sum of the lambdas equal to 1. Right. Now let alpha equal to the sum of the first n minus 1 values. N minus 1 lambda values. Right. So then that will be equal to 1 minus the last lambda n value, right? So alpha is the sum of the first n minus 1 lambda values. So therefore, that will be equal to 1 minus lambda n, right? Now, if this lambda n is equal to 1, in that case, alpha will be equal to 0, because this lambda i's are greater than or equal to 0. That will satisfy alpha will be equal to 0 because there will be no negative values. Sum of non-negative values will be equal to 0 only if and only if all the individual values are equal to 0. So if, for example, if lambda n is equal to 0, that means all the other lambdas must be equal to 0. Therefore, in that case, g of sum of lambda xi will be equal to just g evaluated at xn, because all the other lambdas are 0. So only I equal to n case will be coming. So in that case, g of uh, 1 times xn, which is the same as lambda sum of lambda I times gxi, because again all the lambda i's up to n minus 1 will be 0. So there from this you will get only 1 times gxn. So therefore, if that particular case, if lambda n is equal to 1, automatically the Johnson's inequality for case n is satisfied. So that's a trivial case. Let us now consider a situation where lambda n is not equal to 1. So if lambda n is not equal to 1, then this alpha will not be equal to 0, right? So it will be greater than 0. So now we will look at this quantity, I from 1 to n, lambda I xi. You can write down that one like this because alpha is greater than 0 now. You can divide by alpha, right? So you can easily see that this quantity is equal to this quantity plus lambda n times xn, right? So we are considering the sum up to n minus 1, but with this divisor alpha and multiplied by alpha to cancel it off. So therefore, this quantity is the same as this one. And you can see that now it is like something like alpha times some y plus alpha lambda n times another quantity, where now alpha plus lambda n will be equal to 1, right? So we, according to the way that we selected, alpha plus lambda n is equal to 1, right? So we are now back in the situation like n equal to 2 case, right? So you are considering two constants, two quantities, y and xn with some weights, for example, alpha and lambda n, where the sum of the weights equal to 1. So by the definition of the convexity of G, then we can definitely say G evaluated that this thing should be less than or equal to alpha times G evaluated at this point plus lambda n times G evaluated at xn. That is coming from the property of the convexity. So therefore, G evaluated at that point should be equal to alpha times G evaluated at y plus lambda n times G evaluated at xn, right? But the summation, this summation here, lambda I divided by alpha, if you consider this up to n minus 1, is going to be equal to 1 according to the way that we defined alpha, right? Alpha is equal to this quantity. Therefore, this quantity alpha, that quantity divided by alpha will be equal to 1, right? So therefore, if you consider the hypothesis that we had for n minus 1 situation, we are assuming that the inequality is true for n minus 1 point. So therefore, if you consider G evaluated at this point here with n minus 1 point should be less than or equal to lambda I divided by alpha, those are the weights, times gxi summed over I from 1 to n minus 1. So that is coming from the assumption that we are assuming the, right? So these are like something like those mu's that we had in the n minus 1 case, where the sum of these quantities is equal to 1. So therefore, this is true if our assumption regarding the case n minus 1 was correct, right? So therefore, you can see that G of evaluated at this point is less than or equal to this quantity here, and which is equal to this quantity. So therefore, that again proves that the inequality is true for case n, right? So that's how we prove the Jensen's inequality by induction, right? So please go through it to understand. It's not difficult to see, right? So now we are coming to the statistical version of this, right? We can actually get the statistical version for discrete random variable directly using the Jensen's inequality. So let us look at that first. So let x be a discrete random variable taking the values x1 up to xn. Right? We are considering a finite domain case with some probabilities p1, p2, p3 up to pn, where those, if there are only n possible values, the probability of each value is given by pn, then we know the sum of those values, all the probabilities are greater than or equal to 0 by property of the probability, and we know the sum of the probabilities should be equal to 1. So therefore, we are in a situation with several x's possible for the random variable x and several weights, for example, which are greater than or equal to 0 and sum into 1. Therefore, directly we can apply the Jensen's inequality. So that will give you this thing. If G is convex, then G evaluated at sum of Pixi should be less than or equal to sum of Pigxi. Right. Now, if you consider this quantity, this is actually the, by definition of the expected value, this will be expected value of x. So what you have here is G of expected value of x. On the other hand, this side is the expected value of gx. Right? Expected value of gx is given by this expression. So therefore, what you have here is the expected value of gx. So that gives you the statistical version of the Jensen's inequality. G of expected value of x is less than or equal to expected value of gx. Right, where now x is a discrete random variable. So therefore, you can see that the discrete, this is the Jensen's inequality for a discrete random variable, right? Random variable application of the Jensen's inequality for a discrete random variable. But it is only for a discrete case. So let us look at for any random variable, discrete or continuous. Also, we can prove it. So this is the common statistical version of the Jensen's inequality. Let x be a random variable, so it can be discrete or continuous, such that expected value of x is So this can be applied, of course, only if x is expected value of x only if x is expected value of x exists. So, for example, like random variables whose distribution is like Cauchy, this will not be valid, right? Given that expected value of x exists, and if g is a convex function, and if expected value of gx also exists, then we can say g evaluated at expected value of x should be less than or equal to the expected value of g of x. Notice here, g of capital X is a random variable. That's why we are able to talk about expected value. Here, g of expected value, here expected value of x is a random variable. Gx is also a random variable. So because x is a random variable, we can talk about the expected value of x, and expected value of x is a constant, it's a real number. So we are looking at here g evaluated at a real number. On this side here, gx is a random variable, and we are considering the expected value of that random variable. So expected value of a random variable is again a real number. So we are just here, this side is a real number, this side is a real number. So this inequality always is meaningful. So if G is strictly convex, equality holds if and only if X is a constant in that case. So this equality will happen only if x is a constant. So in that case, actually, x is not a random variable. Probability x equal to 0 is equal to 1. So in that case, we call x is a degenerate random variable. Oh, it's actually a constant, almost a constant, right? So probability x equal to c is equal to 1. Right? So there can be situations, values which x is not equal to c, but then the probability at those points will be 0. Right? So that's what we mean by this degenerative random variable. So it's almost like a constant. Right. So how do we prove this one for general random variable, discrete or continuous? We can easily prove this one by considering the second characterization of the convex function. Right? Remember, if G is convex and differentiable, then the graph lies above every tangent line. Right? If you draw the tangent line to the graph at any point, and then the whole graph always lies above the points on the tangent line. So therefore, we can say that if you consider a particular point, say x naught, say let's take x naught to be the expected value of the random variable x, which is usually denoted by mu. So let us consider that particular point and the tangent at that particular point. So then for that particular point also, then gx should be greater than or equal to the corresponding point on the tangents, which is given by gx naught plus x minus x naught g dash x naught. So this is the point on the tangent drawn at x naught, but this is the point on that tangent at x equal to simple x. So this is the point when x equal to simple x on the graph. So the graph is always above the corresponding tangent point. Therefore, gx is greater than or equal to that. Right. So if you put these particular values, in that case, we get gx is greater than or equal to g evaluated at value mu plus x minus mu g dash mu. Right. So this is the important one that we want to consider. Right. Now, remember that this x is a real number. Mu is a real number. G is just a mathematical function. So how can we now relate this to a random variable? Remember, random variable is also a function, right? We earlier learned this. Random variable is a function defined from the sample space into the real line. So therefore, even though we usually write down as x, but it really means x at some point omega, where omega has to be an element of the sample space. So now X is a random variable. So if you consider some real number simple X, we can say, for example, we can consider a real number simple X where X, capital X omega is equal to that real number simple X, right? So x omega will be a real number, and suppose x omega is equal to simple x, right? If you consider any point on the in the sample space, not a point actually, an element in the sample space, say omega, then when you evaluate the function x on that uh, element omega, you will get a real number, and suppose that real number is x. So then uh, we should be able to write down the previous expression, this expression, for that x also, if g is a convex function. So therefore, g at that simple x, which is now equal to x omega, greater than or equal to g mu plus, and then simple x, which is now x capital X omega minus mu g dash mu, right? So this is like what? This is like saying the g of x omega. So this is like gx. So this is again a random variable, right? Usually we uh, denote it by x omitting omega. So then we know it's a random variable. So you can consider it as a random variable gx. And this side is again a random variable. This is a constant, but this is a random variable. This is a constant, this is a constant. So whole thing is a random variable. So this is like saying some random variable is greater than or equal to another random variable w, right? So now, uh, if you say, when do you say one random variable is greater than or equal to another random variable? By definition, we say one random variable u is greater than or equal to another random variable if, right, these both random variables have to be defined on the same sample space. Otherwise, this is not going to be meaningful, right? So we say u greater than or equal to w if u omega is greater than or equal to w omega for every omega in the sample space. That is what we mean by saying that one random variable is greater than the other random variable. What you have here when g is a convex function, right? So this means u omega is greater than or equal to w omega for every omega in the sample space. Now, so if you can, therefore, we can consider u and w both at the same omega, where omega is an element in the sample space. So let us define, so for example, the difference between these two. D omega is equal to u omega minus w omega. Then, of course, d omega have to be greater than or equal to 0 for every omega in the sample space. So if d omega is greater than or equal to 0 for every omega in the sample space, then the expected value of d must be greater than or equal to 0, right? Because expected value of d is equal to d omega values times the corresponding probabilities added all together, right? So probabilities are always greater than or equal to 0. If the d omega values are also greater than 0, then when you take the sum of d omega times the corresponding probabilities, always you are going to get, you are not going to get a negative value. It's always greater than or equal to 0. So d omega will be always greater than or equal to 0. So that implies that expected value of expected value of d is greater than or equal to 0. That means expected value of this thing is greater than or equal to 0. That means expected value of u is greater than or equal to expected value of w. That means expected value of g of x is greater than or equal to expected value of this thing. So that's how we can connect the original mathematical uh, inequality coming from the definition of the convexity to now random variables. right? So we can have this expression with now random variable. Expected value of gx is greater than or equal to expected value of this one. So now we will just use the property of the expected value. So this is a constant, this is random, this is constant, this is again a constant. So therefore, this side we can write down as expected value of a constant plus constant times a random variable. So that will be equal to this constant plus this constant times the expected value of this random variable. So the left hand side stays the same, but the right hand side becomes g mu plus this constant time the expected value of x minus mu, which is equal to this part here is equal to expected value of x minus mu. But mu was the expected value of x. We selected mu to be the expected value of x. So therefore, this part will be 0. So therefore, this whole thing will be 0. So you can see that you get expected. Therefore, you will see that this thing is greater than or equal to g of mu. Expected value of g of x is greater than or equal to g of mu, but mu is equal to expected value of x. So therefore, you get this expression, expected value of g evaluated at the random variable x greater than or equal to g evaluated at expected value of x. Right? So you have to be careful when you write down these things. Remember the random variables. At expected value of gx. Gx is a random variable, but when you consider the expected value of that, that becomes, whole thing becomes a real number. Here g is a function, but expected value x is a random variable. Therefore, expected value of x is a real number. So you are looking at g evaluated at that real. So this is perfectly meaningful. That's going back to the mathematical Jensen's inequality. Right. So that's the Jensen's inequality. This is very useful actually. Uh, so let us look at some examples. Right. So remember, this is valid only when the corresponding function g is convex. So let us look at some convex functions. So the first one I'm going to look at is the square function. Gx is equal to x square. Right? So you know the function is like this. So it's convex, right? You can definitely see that second derivative is equal to 2, that is positive, therefore it's convex. So you can, by looking at the graph also, you can see that it's convex. So therefore, if you consider g x equal to x square, then you should be able to say that g expected value of gx is greater than or equal to g of the expected value. So that means expected value of x square is greater than or equal to expected value of x square, right? Whole thing is square. Sometimes people write down it as e square x. E square x means ex whole thing square. Right. So that is one important thing to remember. Especially, it's not equal. Expected value of x square is not equal to expected value of x square. That is generally you have to know. But the exact expression is it's greater than or equal. It's never equal actually. So it's greater than or equal. Right. Not only it will be equal only if this thing is equal to a constant with probability 1. But, for general random variables is greater than always. Expected value of x square is greater than expected value of x whole thing square. Let's look at this convex function gx equal to ex. Again, you can see that the second derivative is again ex. It's always greater than 0 when x is any real number, uh, unless x goes to negative infinity, then only it becomes 0. Otherwise, for any real number greater than negative infinity, it's positive. Therefore, we should be able to write down again expected value of gx is greater than or equal to g of expected value of x. So that is e to the power expected value of x. Right. So that is another example. If you consider gx equal to 1 over x, again, you can see that is convex on this part of the real line from 0 to infinity, exclusive 0, excluding 0. On that part, this is convex. You can see that this is always positive on this subset of the real line. Therefore, when x greater than 0, that means when x omega is in this interval, expected value of x is greater than or equal to, expected value of 1 over x is greater than or equal to 1 over expected value. Expected value of gx, g of capital X is greater than or equal to 1 over g of uh, Ex, so that is equal to 1 over expected value of x. And this is another example. If you consider the gx equal to negative log x on this subset of the real line from 0 to infinity excluding 0, again, you can see that's a convex function. And therefore, expected value of negative log of x should be greater than or equal to negative log of expected value. And if you take if you consider the log of x, actually, it's going to be concave. It's a concave function in on this line. So in that case, actually, it will be the inequality will be on the other way around. Expected value of log x will be less than or equal to log of expected value of x. But this is the one that is coming directly from the Jensen's inequality. And there is another convex function, gx is equal to absolute x. So that is a convex function very clearly. So therefore, expected value of absolute value of x should be greater than or equal to the absolute value of expected value, right? And for a power function, for any r greater than or equal to 1, this is called the power function, gx equal to rth value of x, absolute value of x, is a convex function. Therefore, you can say that expected value of x to the power r is greater than or equal to expected value rth power of the expected value of x, absolute value. So a particular case we have already looked at when r is equal to 2, expected value of x square is greater than or equal to the square of the expected value of x. We have already looked at that. So that's a particular case for this example when r is equal to 2. Right. Now I'm going to again emphasize some two examples where some people, most of the students I have seen making this mistake, right? Suppose we wish to test, right? This is related to something called test of hypothesis. We will be discussing these things later. But I have seen in many situations people making this error. So what is this error? Suppose somebody wants to check whether the mean of one random variable is equal to the mean of another random variable, right? Mean of x, that is expected value of x, equal to the mean of another random variable, expected value of y. So if you want to test this hypothesis, in some particular, under some particular assumptions, there are some standard tests. For example, if x and y are normally distributed, there is a test called two sample t-test that can be used to check whether this the mean of x is equal to mean of y, right? So in that case, we here we are talking about the population mean, another population mean, but we don't have the data for the whole population usually. Therefore, what we do is we take a sample from each population, and then using the sample, we carry out the sample test, right? Uh, So if the x and y both are normally distributed, then of course there is a standard test. But if x and y are, or maybe one of those is not normally distributed, then the t-test is not valid, especially if the sample size is small, this t-test is not valid. So what some people do in that case is they do some transformation. For example, some people sometimes try take log of x and log of y, and then sometimes they become log of x becomes approximately normal, not exactly normal, but approximately normal distributed, and log y becomes approximately normal. And therefore, some people, instead of testing this one, because now log of x is approximately normal, log of y is approximately normal, they can test this, whether expected value of log of x is equal to expected value of log of y, using again two sample t-test. So therefore, instead of this, they test this hypothesis using the sample test. And then if, for example, if the test says that expected value of log x is equal to expected value of log y, then they conclude that saying that implies expected value of x is equal to expected value of y, which is actually a wrong conclusion. Even if expected value of log of x is equal to expected value of log of y, that doesn't imply directly that expected value of x is equal to expected value of y, uh, because you saw that expected value of log of x is not equal to expected value of x, right? Expected value of log of x is less than or equal to expected value of x, you saw in the previous example. Right? And similarly, this quantity is less than or equal to expected value of y. So therefore, this equal doesn't imply this equality. So that is an important thing to remember. If you see some, or if, sometimes you might see these kind of things in research papers, and because some people don't understand, even the reviewers don't know these things. They think that if log of x is equal to, if expected value of log of x is equal to expected value of log of y, that implies that. And people say, you will see this kind of errors in research, even in research papers. Both the writer or the author or know the reviewer knows about these kind of things. So that is a common mistake made by some people. Uh, there's another mistake that I see frequently in regression analysis. In the regression analysis, what we do is we try to find out a relationship between one random variable y and another variable x. Right. So we try to fit a model for the expected value of y. We try to write down expected value of y in terms of as a linear function of x. But usually, when in the uh, standard regression, there's an assumption that y value for a given x, for a fixed x, is normally distributed, right? But there are situations where for a given x, y is not normally distributed, and therefore people are not able to directly use the standard regression method to find out the model the relationship. For example, y is equal to alpha plus beta x. So in that kind of situation, sometimes people transform your y value, their y values, taking log of y, and then they might see that for a given x, log of y is normally distributed approximately. For a given x, log of y is approximately normally distributed, and therefore they consider, instead of expected value of y is equal to alpha plus beta x, they consider this model, expected value of log y is equal to alpha plus beta x. This can be considered as a standard regression in that case, because log y may be a new random variable, right? So they may be able to fit this model. But the the mistake they make is that when they want to get the expected value, they write down expected value is equal to exponential of this thing, right? If you just mathematically consider, uh, for example, log y is equal to this thing, then y will be equal to e to the power alpha plus beta epsilon. So they think that is valid for the expected value also, which is not really correct because we saw earlier expected value of log of y is less than or equal to expected value of y. And therefore, you cannot write down that expected value of y is equal to this thing, right? E to the power alpha plus beta x will be equal to only uh, expected value of log of y is equal to this one. But that doesn't imply that expected value of y is equal to, you cannot take the log outside of the expected value and then take the exponential. That's not possible. That's not valid for this random variable. And therefore, this thing will not imply this expression, right? So therefore, that don't make that mistake. And even sometimes you will see this kind of mistakes in research papers because both the author and the reviewer don't know these things, right? I think that's a good place to take a short break. I will stop my recording here.